Uh, a very good morning, good evening to all those who have joined us today in attending this special public lecture by Professor David Winlin, Nobel Laureate Physics 2012, who have joined us from University of Oregon. And this special public lecture on atomic clocks is jointly organized by the National Academy of Sciences India Delhi chapter and the Science Foundation and Ministry of Education Institution Innovation Council, the Dayal Upadhyaya College, University of Delhi, under the aegis of the Department of Biotechnology's Star College program. And before inviting Professor David to deliver his talk, I would first like to acknowledge the Academy under whose banner we are organizing this webinar. So, the National Academy of Sciences India was founded in the year 1930 with the objectives to provide a national forum for the publication of research work carried out by Indian scientists and to provide opportunities for exchange of views amongst them. And Professor Meghnad Saha was one of the founders and also the first president of the academy, which was established in 1930. The National Academy of Sciences India Delhi chapter was founded in April 2008 under the able leadership of Professor Ajoy Khatak, who's the founder chairperson of the chapter and has continued to be the chairperson from 2008 to 2020. And after his elevation as the president of the National Academy of Sciences India, now Professor Anurag Sharma, who is a faculty member at Department of Physics, IIT Delhi, is currently the chairperson of the NASI Delhi chapter. In the series, in the last 1 year, we have been very fortunate in hosting the Nobel Laureates lecture series, in which the first talk was given by Professor Jean-Marie Lehn from University of Strasbourg on steps towards complex matter, that is chemistry, on September 21st. And then in the October 2020, Professor William D. Phillips, a Nobel laureate from Quantum Institute, National Institute of Standards and Technology, University of Maryland, delivered a talk on a new measure, the reforms of the International System of Units. On January 13th, 2021, Sir Anthony J. Leggett, Nobel laureate physics from University of Illinois, delivered a special public lecture on Does the Everyday World Really Obey Quantum Mechanics? And now, continuing with the same series, we have with us today Professor David Winlin, who will be delivering his talk on atomic clocks. Professor David received his BA degree from the University of California, Berkeley in 1965 and his PhD from Harvard University in 1970. Following a postdoctoral position at the University of Washington in 1975, he joined the Time and Frequency Division of the National Institute of Standards and Technology, then called the National Bureau of Standards, where he served as leader of an experimental group working with trapped atomic ions until the end of 2017. His research focuses on quantum state manipulation of atomic and atomic-like systems with applications towards quantum information, including quantum computation and quantum limited metrology. For example, in 1995, the NIST group demonstrated the first deterministic multi-qubit logic gates using individual quantum systems. He also holds a research associate position at NIST and an adjunct professor position at the University of Colorado. Professor David is a fellow of the American Physical Society and the Optical Society of America, and is a member of the National Academy of Sciences, and has served on several advisory boards and conference organizing committees. Starting in the late 1970s, he has designed ingenious experiments to study the quantum phenomena where matter and light interact. Using electric fields, he has successfully captured electrically charged atoms or ions in a kind of trap and studied them with the help of small packets of light or photons. He has received several honors, including sharing with Sir Hero Paris, College de Paris, France, Paris, the 2012 Nobel Prize in Physics for the manipulation and measurement of individual quantum systems. With this, I now request Professor David to kindly share his screen and deliver his talk.
Okay, let's see. Okay, I think we're set here. Let's see.
So maybe if you can go to the first slide. Yeah, absolutely perfect. Sure.
So just to summarize here, I'm just going to cover, first of all, why precise clocks? Why do we want precise clocks? I'm going to give a few ideas, the basic ideas about atomic clocks. And if I do it right, it's not really that complicated. And more recently, in the last 10 years or so, we've gone from microwave clocks operating at microwave frequencies to clocks operating at optical frequencies. And I'll say a little bit about that. And then near the end, I'll kind of give the status of things and then, where the future might go. And then also for the students, they sometimes appreciate seeing a bit more of my past, my growing up into physics. And so I'll start now. And so certainly one of the things that we want precise clocks for has been true for centuries, and that is in navigation. So for, the last several centuries, as sailors at sea, to find their latitude, they would find, using a sextant, they would measure the angle between the local level and the direction of the fixed star, say the North Star in the northern hemisphere. And so that way that would give them latitude. But for longitude, the idea is exactly the same, but to find out where they are on the surface of the Earth, they needed to know time, because astronomers had made tables, tabulated the apparent positions of stars versus time, but then the sailors needed to know what time it was to be able to calculate longitude. So these days, of course, though, it's quite a bit different. Modern navigation, and GPS is a good example. The basic idea here is pretty simple as well. It's a little different, but the idea is, suppose you on Earth have a clock and it's synchronized with a clock on board a satellite. And so by some protocol, it's certainly more complicated than what I'll say here, but the basic idea is, suppose you agree that the satellite will emit a pulse on every second tick. And of course, it takes the speed of light times the time, the time given by the speed of light to reach you on Earth. And so by measured, a simple expression there says that the length between you and the satellite is given by the speed of light times the time delay. And to give an idea of the precisions that can be achieved if we can have the clock synchronized to about a nanosecond, then the imprecision in this length would be around 30 centimeters. And this sort of 1 nanosecond per day is about, expressed fractionally, is about uncertainty about part in 10 to the 14th. And this also then, it also states the required frequency precision, the clock rate of our clocks that must be maintained. It's the same fractional precision that's required. So of course, it's a little more complicated than that. There's a network of satellites and the system's somewhat overdetermined. The various clocks can check each other and improve their synchronization and so on. But the idea is then if you have at least 4 satellites, they can give the distance from the satellites and also the time, the absolute time. And so this is how navigation in 3D is done. So what about clocks? And I think the ideas are, are as simple as the early days, and the ideas that need some periodic event generator, and it'll be an oscillator in our case, and then a counter, and basically you just count the cycles of this event generator to generate time. And traditionally, the periodic event generators have been first the rotation of the Earth, and then certainly starting in the late 18th century, the clocks were, the pendulum clocks were invented, and they actually by the early 1920s and 1930s, they were actually extremely precise, not as good as our atomic clocks, but still extremely precise. So what we're going to use those for the event generator is the oscillation of atoms, and in particular, of course, our classical picture in the lower left there is we first learned about electrons orbiting around the nucleus, and of course, when we learn quantum mechanics, things aren't quite so simple, but the ideas are pretty similar. We have to talk about the wave function of, say, an electron about the center of an atom. And what I show in the picture on the right there is sort of the oscillating electric charge density of an electric dipole transition. And of course, Max Planck taught us long ago that the frequency then of this oscillating dipole and the radiation that's given off is given by the energy level difference between two levels whose superposition forms this oscillation, and divided by Planck's constant. And so one version of a clock that's certainly been around for quite a while is to actually, this electric dipole will radiate, and if we just pick up the radiation that's being emitted, and we just count cycles of that to determine this fundamental oscillation frequency, F naught. And certainly in earliest precise clocks like this were masers or lasers, and everybody knows what lasers, and maybe not everybody knows what a maser is. Basically, they work on exactly the same principle. M stands for microwave, and L, of course, stands for light. So it's just the same principle, but oscillating at different frequency. So the idea is then, as I say, we just count the cycles of the radiation, and this generates time, given by the expression up here, including Planck's constant. So actually, but a bit of a problem with a maser and a laser is that, maser and laser cavities, they're another oscillator, and they actually couple to the atom, and their frequency can't be tuned exactly, and the frequency mistuning of the cavity, either microwave or laser, can pull the frequency of the atomic transition. So to avoid that, the more common mode of operation is we first have our atoms and we initialize them in the ground state, and then we apply radiation near the transition frequency for a certain amount of time. And then we measure the probability of the atom having made the transition from the lower level up to the upper level, which I've labeled 2 here. And when when the transition probability is maximum, then we know that the laser or maser frequency is equal to the fundamental frequency given by Planck's constant. And so then when that condition is met, we just count cycles of the oscillator rather than cycles of the radiation emitted by the atoms. So why atoms? And just to give you a rough idea, a few things we have to consider are environmental factors. So for the pendulum clock for low amplitudes, I give the frequency of oscillation there. And I'm not going to go through this calculation, but sketch out the ideas. So one thing with the pendulum clock we have to worry about is temperature. If the temperature changes, then even with a very good low expansion material, where the expansion coefficient, the fractional change per degree C is about a part in 10 to the 8. That's a very good material. The frequency change given by the above expression is about a change of about 5 parts in 10 to the 9th per degree C. And the idea there is that as the temperature, say that as the temperature goes up, the length, the pendulum bob extends slightly, and that causes the frequency to slow down because of this, because of the expression above there. So what about atoms? And so we typically think about having atoms in some kind of container. Certainly in the early days of atomic clocks, the atoms were neutral atoms, and they were stored inside of a cell which was coated with some material where the atoms wouldn't stick. And the thing we have to worry about there fundamentally, I mean, there's other possible environmental temperature effects, but the fundamental thing we have to worry about was given to us by Einstein, and that's his relativistic time dilation. And you know, of course, what the amazing thing about Einstein is, it wasn't like you know, what he realized, it wasn't like our clock running slower because the length of the pendulum was changing. What he showed us was that time was actually running slower for moving object relative to us as observers in the lab. And I just, those expressions on the right there, I'm not going to go through them, but just to give you a rough idea for, because of this time dilation, for a mass of 133 cesium, the fractional change in temperature is about a part in 10 to the 15 per degree C, so about 7 orders of magnitude less sensitive than the pendulum clock. And what about reproducibility? Well, for the pendulum clock, of course, it depends on manufacturing tolerances. And of course, it also depends on the local value of G and where, say, on the bearing that holds the pendulum, you know, that could cause the effective length to change a little bit, and that would be a problem. The nice thing about atoms is that for all atoms of a particular kind, say cesium-133, as far as we know, they're absolutely identical. And in fact, they don't wear out. We can use the same atoms for as long as we can keep them around. They don't change. So just to come back to why I'm choosing cesium here, as I think many of you know, the internationally agreed definition of the second corresponds to about 9 billion and so many cycles of the oscillation of the cesium hyperfine transition. And the hyperfine transition, if you don't know that term, it's basically, it's the separation of the two energy levels that make up the standard are given by whether the electron's magnetic moment is aligned or anti-aligned with the cesium nucleus. And so those are the two energy levels, and that's what gives this roughly 9 gigahertz signal. Anyway, this was the definition of the second, which was adopted in 1967, and it is still the definition. And actually, what we're finding out, and I think will show you, is that the optical clocks that we're making now are actually better. They work better than the cesium clock. But there's lots of tradition here, and so people will probably change the definition someday. But even with our optical clocks, there's no clear best one, and so there's no reason to change the definition right now. So we still reference back to the cesium clock transition. So in the experiments I'll describe, we used charged atomic ions, and people also use neutral atoms in traps. But the idea here is that, and what I'm showing on this cartoon here is that these were traps developed by Hans Stamos and Wolfgang Paul. They did most of the early development on these, and they actually shared the Nobel Prize in 1989 primarily for this creation of these traps. And the idea of this simple version, this simple geometry I'm showing here, is that we apply a combination of oscillating and static electric potentials to these electrodes, and it basically creates near the center of this device. It creates a 3-dimensional harmonic well. And it's not immediately apparent how that works, but it's actually fairly straightforward. It just takes a little time to convince you of that. It's sort of an analog, and 2D is, you can think of a marble just rolling back and forth in the bowl. Dr. Saxena, can you clear off the pictures off of my screen? Because the pictures of people off my screen, or no? I can, it's covering up part of my slides, that's all.
Sir, what kind of pictures are there?
Well, I see me, I see the symbol for your college, and then I see a...
Okay, sir, there is an option on that. If you can see view and on that in the Zoom, because I can check it out from my end, but and when you're, have you put it in the slideshow?
No. Yeah, it's in the slideshow now, but it's being covered.
Okay,
covered up by these.
So on the right hand side,
yeah, it says more.
There must be a minus sign. If you just click on it, it can minimize it.
I don't see the minus sign. Look, it's not. It isn't worth.
But we are able to see. We are able to see your slides perfectly fine, sir.
Yeah. Okay. It's just these other pictures are covering up my slides.
If you can just drag it on the right hand side. If you can just click on it and drag it on the right hand side, sir, maybe.
Click what on the right hand side?
Okay, those boxes, they are still there.
Yeah, but I'm going to let it go. I don't see anything where I can minimize.
Okay, but we can see all the pictures, everything absolutely clear.
Then I'll be fine then. I'll just continue.
Sure, fine.
So anyway, so one thing, in around 1980, we had been working on atomic ions as clocks before then. But we realized, like other people did, that what we'd like to do in principle is go much higher frequency of the transitions. And the simple reason for that is if we can, for these higher frequencies, we can basically just divide any unit of time, say the second, into finer and finer intervals. And so what I show there, and that's one of the main advantages, to get a very fast tick rate. So I show this mercury transition in mercury, which is a little over 10 to the 15 hertz. That's about 1 million times higher than the cesium frequency. Then we can just define the second sequence to finer and finer increments. So what I show there is the cartoon of a single mercury ion at the center of this ion trap. And the radiation that for the clock transition labeled with the levels 1 and 2, and I give the atomic notation there as well, is in the ultraviolet. Anyway, so we basically, as using the protocol I showed you before, we start the atom in the ground state and then radiate it and try to promote it to the upper level there. So of course, for precision, we want this range of absorption to be as narrow as possible. That just gives good discrimination on where our clock laser is tuned. For mercury, it's a pretty good choice. The lifetime of this upper level 2, is about 1/10 of a second. So the range of frequencies over which the atom will absorb is close, around 10 hertz, a little less. But anyway, we can get very high. So in that case, the fractional resolution is about a part in 10 to the 14. So how do we detect? I gave you the basic ideas. We want to look at transitions between the ground and excited state of a clock transition. And so the way we do it in mercury, and actually all these optical clock transitions of the ions we're using, is that we start the atom in the atomic notation in the S state, and then we apply radiation at the clock frequency. So on this transition here, and then let's suppose that radiation is not tuned to the transition frequency. Then when we turn that laser off, we can we can turn on another laser on a laser onto another transition. And the property of this transition is the upper level has an extremely short lifetime. So we can scatter up to about 20 million photons per second. And even if we only capture a small number of those scattered photons, we can easily tell when the atom is in the ground state of the clock transition. On the other hand, if the clock laser is tuned correctly, then we'll promote the atom from the ground S state up to the upper clock level, this D5 has state. And then when we turn on this detection laser, we don't see any scattering. And so because there's such strong scattering when it's in the S state and extremely little just from stray light when it's in the D state, we can essentially tell with 100% efficiency which state the clock states are in. So for Mercury, I can't read what things are covering this thing up here. Anyway, for Mercury, this transition is at about 194 nanometers, and actually, in principle, in some sense, we can see the radiation that's emitted by the atom when it's in the S state. And I show a picture we make, and of course, this laser, the light is in the ultraviolet, so you can't see it with your eye. But we have essentially just a ultraviolet sensitive video camera, and we can make a picture like I've shown on the lower right. So one interesting thing about this picture is that the size of the atom that you see, or the image that you see there, is actually about 500 times larger than the actual size of the wave packet of the mercury. And then the image is just limited by the quality of the optics. So another thing we've been using for a long time now is that when the ion scatters the 194 nanometer light, it feels radiation pressure. In other words, it feels recoil from the photons that are scattered. And this radiation pressure can actually be used to cool the atoms. And the idea is actually very simple there. If we just tune the radiation of the detection laser slightly below the resonance frequency, then when the atom moves against the laser beam, it scatters photons at a higher rate as opposed to when it's moving away. It's basically, this is just the first order Doppler shift. So when it's moving towards the atoms scatter more and they feel higher radiation pressure. And this fact that the radiation pressure acts against their motion will cool them down. And just to give you a rough idea, the performance we can get with this idea is that in these early experiments, we started, the atoms would be at essentially the temperature of the lab, room temperature, and this radiation pressure laser cooling would get the effective atom temperature down to about 1 millikelvin. And of course, the main reason this is interesting is that this highly suppresses the time dilation shift that I described earlier. So this is a picture not long after we did these first cooling experiments. The person on the right there, Bob Drollinger, he and I were the first ones to do these cooling experiments. And Jim Berquist, as I mentioned, was really kind of guiding this clock experiment. And Wayne Atono had joined us not just a year or two before this, and was kind of our expert theorist, and did a lot of the theory for the experiments we did through the years. So just to summarize, I'm going to say a little bit about, we started this project on Mercury in 1981. And some of the nice features we were able to realize, of course, just the trapping alone, just the fact that the atoms are trapped, it means their mean velocity goes to 0. And so the first order Doppler shift goes to 0 as well. And as I explained, the laser cooling can drastically reduce the time dilation shift. There's also, in the later experiments, we put the trap in high vacuum, mainly achieved with a low temperature of about 4 Kelvin liquid helium temperature. And what this does, it basically freezes out all the background gas, so we don't have to worry about shift to the collisions. Also, another interesting effect is that, the so-called black body radiation, thermal radiation, for example, in the room, it's in the infrared, but the electric fields from the thermal radiation in the room is actually, the electric field is about 10 volts per centimeter. So it's actually not a small effect. Anyway, we have to, what was nice about going to low temperatures, this effect scales, the radiation scales as temperature to the fourth power. So by going from 300 to 4 Kelvin, we drastically reduce the black body shift. So anyway, so 2006, as I say, we started this project in 1980. And a lot of things we did that I'm not going to describe here, but what a nice kind of plateau to reach was in 1986. This project led by Jim Berkowitz. It was the first time a clock had ever outperformed the cesium clock, since the cesium clock was defined as the standard. And so this kind of set the stage for improvements, I think, using atomic clocks, or rather optical transitions. So there's many effects that we have to worry about. And some of the more common ones are ambient electric and magnetic fields. I mentioned thermal radiation, but the magnetic and electric fields are always around when you have metal surfaces and so on. So we basically measure other transitions in the ion that are very sensitive to these the electric and magnetic fields, and then we can calibrate out the effect on the clock transition. Of course, the more interesting effects are relativity, and I've already described the time dilation shift due to atomic motion. But that Einstein again came into play because what he told us about a second kind of time dilation shift. And it basically what he shows is that clocks run slower, or excuse me, time runs slower in stronger gravitational potentials. And so this is an effect we have to worry about, since our clocks are on the surface of the Earth. And just to give an idea of the effect on the surface of the Earth is, so the red shift, we call it red just because the frequency is being downshifted by the gravitational potential, is almost a part in 10 to the 8. And so since the precisions of the clock are so much higher than this, we clearly have to worry about this. And so one way we have to worry about this is when we compare clocks, they may be at different heights, and we have to know the heights. If we're comparing between two labs, we have to know the height the difference in height between the two labs. Now, this is a small effect on a human scale, and just to give you an idea how small it is, at least why we don't normally experience this, here's a little story. So suppose you and a twin sibling were separated at birth, and you live at sea level, and your twin lives in Boulder, where NIST, the NIST lab I work in, is about 1.6 kilometers above sea level. It turns out after 80 years, your twin will only be about a millisecond older than you. So on a human scale, it's a very small effect. You just never feel that, of course. And so, but with our accurate clocks, we have to worry about it. And so anyway, just for fun, we did an experiment demonstrating this gravitational redshift. So this shows we actually switched to aluminum ions in our later work. It was nothing fundamental, but aluminum had some nice properties that allowed us to reach higher precisions. One thing I mentioned is that, for example, the Mercury lifetime of the upper state was about 1/10 of a second. The upper state of the clock transition in aluminum is about 20 seconds. And so we get much finer resolution on the clock transition. Anyway, so obviously it doesn't look much like a clock here. It's hard to see this. You can see maybe this aluminum tube here houses the vacuum for the ion, and all this other stuff is optics that control the lasers that we use in the experiments. So anyway, there was another clock, essentially just like this one, in the room off to the right, next door room off to the right in this picture. And the clocks were at the same height above the floor. And so we could measure the ratio of the frequencies of these two clocks. And it was basically 1 to about a part in 10 to the 18. So what in the lab that I'm showing the pictures of, this was James Chow, who was one of the main people working on this experiment at that time. So you can see what he's done is he's put some jacks underneath this table here to raise the clock up in this room. And so he raises it up, oops, I did too quickly there. So he raises it up about 33 centimeters, and we could measure the frequency shift. It's about 40 parts in 10 to the 18th. So it is with the precisions we achieve now, we do have to worry about these small changes in heights when we when we compare clocks. So anyway, what's the state of play right now? And certainly, I've just to talk about the ion experiments at NIST. There's many other ion experiments, and there's many neutral atom experiments that have very similar performance to what I talked about here. So, and that's why I said earlier that there's no obvious choice if you were to try to choose a new definition of a second. There's many good optical clocks now, but the best one, it just isn't clear yet. So anyway, the precision now, the uncertainty, that is all the environmental effects, the relativistic effects and so on, we can measure down to a fractional level of about a part in 10 to the 18. So what's the future? So I talked about how the time dilation shift could be used to measure height differences, and so in some sense we can do navigation down at the 1 centimeter scale. And some people think this might be interesting because, for example, with two clocks where you measure their frequencies, and if one clock, say, is separated by a kilometer from where you are, if it raises up a few centimeters, then by comparing the clock frequencies, you should be able to compare this change in height. In other words, the strain of the Earth. And the reason that might be interesting in a practical scale is that basically Earth strains are pretty much a precursor of earthquakes. And so people have thought that maybe by keeping track of the Earth strains, that maybe such measurements could be useful in earthquake prediction. So there's also, for us, as scientists, there's many things interesting fundamental things we'd like to look at. So and one of the first item there, ask whether the strengths of the basic forces are they constant in time, say the ratio of electromagnetic to strong and so on. And for these different clock transitions, we basically the energy is dependent in different fractions based on the electromagnetic weak and strong transitions. And so by comparing different ion or atom species, we can put a limit on this idea that the forces may be changing, the basic forces may be changing in time. There's been a lot of, with the interest, of course, in gravity wave detection, there's certain models for where you could actually, first of all, you could in principle detect gravity wave detection by looking at relative frequency shifts. And also that people have proposed different ways that dark matter may shift the relative frequencies of two clocks. And it's always been a sport in physics to find possible deviations from Einstein's general relativity. And so far he's been safe for over the last 100 years. So we haven't found anything yet, but just as a scientist, you want to see whether you could uncover something and there may be some new physics that people haven't seen yet. So I just show in this view graph, this was the group I left about the time I left NIST. And you can see there's many people there. So I showed the earlier picture where we started with 4 people, and over the years we gradually grew, and But the main thing I want to say here is that there was a lot of people that contributed to this. The students, the postdocs, visitors, and at this time this picture was taken, there were 5 regular staff in the group. And also, one of the things is I was really great at NIST is we had really great leaders, and a couple of people I can highlight is so during a lot of the time during the time that a lot of this work was done, the laboratory director that is above the time and frequency lab was her name is Catherine Gebbe, and later her position was assumed by Carl Williams, who's now the director. But anyway, Catherine Gebbe's was very popular because her basic motto was that, find good people, give them money, and let them go. And that was, in other words, she never directed us. No, we couldn't do crazy things, but basically we could determine our path from the time I started in '75 until 2017 when I left. So that was just a great experience, and they supported us in part for the experiments. We also had to get outside support. So these are some of the U.S. agencies that supported the work over the last 25, 30 years. So a little bit about my upbringing. So my parents lived through the Great Depression in the U.S. So this was basically, around 10 years starting around 1930. And so they were lucky because they both had jobs. And so, but there was, people that didn't have an education, they lost their jobs and they had, living in poverty. It was really a bad time in the U.S. And so with my parents, they took this lesson to heart. And so basically what they emphasized with me and my sisters, we just, first thing we just needed to keep good grades in school so that we could get into a good college so that we in the future get a good job. And my father, he would also, I was always kind of interested in math, and he would play simple math games when I was very little. He would, just do game in our head, say multiplying and subtracting, dividing numbers, ran rapid succession. And so I remember that we'd do that in the car. So anyway, both my parents were very supportive of my education and actually, maintaining grades in school. I actually always liked school, so that wasn't a big problem. Oops, sorry. And the other thing is I had, because, if I kept my grades up, I had a lot of freedom to explore. So I always liked mechanical things and, started out for me at model airplanes, and I still do model airplanes off and on these days. But anyway, that's what I was really immersed in when I was about 11 years old. Anyway, as I got closer to high school age, my main buddies and I, we were all interested in cars and motorcycles. So in my own case, I was able to get my first car at age 14, and I couldn't drive it. I couldn't drive it until I was 16, but my father, brought it home, and I spent the next year and a half or so tearing it down and fixing up things and building it back up. So anyway, that was my first car, and I finally got to drive it when I was 16. And actually this continued into high school. So this was near the end of my high school years. And these are the buddies I was talking about. And here we were modifying an unfortunate 1936 Ford. But anyway, it was really fun working together. And you might say, well, this is kind of a waste of time. But in fact, one thing I would like to say is just that there was a lot of teamwork involved in this kind of thing. And in fact, working with these guys was very much like working in a physics, at least an experimental lab, because the experiments are complicated enough that you're often working in a team of, say, 3 or 4 people. So this experience was almost directly transportable to my work in a lab and later on. So give you a little idea of my education. So after high school, I went to the University of California, but the first 2 years I went to the Davis campus, which was near where I grew up, Sacramento, California. And this had been primarily an agricultural school, a very good one, but not so strong in the hard sciences. After my final 2 years, I transferred down to University of California, Berkeley, and that was the big physics school. In addition to Caltech and Stanford, it was kind of the physics school on the West Coast. And so because of that, I transferred down, and it turned out in the University of California system, I didn't have to do anything. I just had to sign a form saying I was going to transfer there. So that process was pretty easy. And I had been a math major when I was at the Davis campus, but I switched to physics when I got down to Berkeley. And then for graduate school, I went to Harvard, and then as a postdoc, my Harvard thesis advisor was Norman Ramsey. He's a famous atomic physicist, mostly molecular beams, but he also invented the hydrogen maser, which I worked on those when I was there. And then I did my postdoctoral work at the University of Washington with Hans Dayal, one of the inventors of the ion traps. And so they actually shared, Norman Ramsey, Wolfgang Paul, and Hans Dayal shared the Nobel Prize in 1989 for Ramsey for the development of the masers and the atomic beam methods, and Powell and Dayal for the ion traps. So that's about it, and thanks for listening, and I'll be happy to answer any questions.
Thank you very much, sir. Maybe if you can just stop sharing and
okay.
Yeah. So now are you able to?
Let's see. I see myself. I
okay.
don't see much else. Let me.
Okay.
Now I can see you. Let me try.
You can see me. I think.
I'll just try a gallery view.
Oh, okay. Yes. So that was the view which.
Anyway, I think this probably be fine.
Whoops. This is perfectly fine. Fine. So thank you very much, sir.
Now I lost it, of course.
So there are a few questions which are there. The first one is, does the time dilation also affects the atomic clocks?
Well, that's what I was trying to say. Yeah, that's one of the effects that all atomic clocks, at least all precision atomic clocks, have to worry about. So
okay.
Yes.
So another thing is, the continuous radiation could lead to loss of energy, leading to some deviation in the measurements. Your comments.
I'm not sure I understand that question. I think the picture that I gave is pretty simple. You could say when our ion, say, absorbs radiation, I mean, it's converting the incoming energy to atomic energy level. So there's, I wouldn't say that's a loss. It's just conversion. So, but there's no magic here. We're not, we're always conserving energy somehow. So eventually the atom, in the excited state of its clock transition, will eventually decay back to the ground state and emit a photon.
The next one is, can rubidium be as an alternative instead of cesium in terms
I'm sorry, just I didn't hear the first part of the question.
Can rubidium atoms in place of cesium atoms?
Yeah.
Your comment on that.
So even starting very early in the 60s, I showed a cartoon of atoms being in a cell that was coated with, and actually the first rubidium clocks were based on atoms stored in a glass cell. Their frequency, I forget now, I think it's around 6 gigahertz. I'm forgetting right now. But anyway, the idea was, it was kind of as I showed it in that picture. So, and actually, these days with cesium also, including, pardon me, including with rubidium, they with neutral atoms, one of the ways high precisions are achieved by lengthening the time the atom is is radiating. And so there's what's called the so-called fountain clock. And so in those experiments, a group of cesium or rubidium atoms are cooled down to a very low temperature, even lower than what I talked about with mercury. And then the atoms are launched upward, and when they go up, and then they come back down. But while they're doing this trajectory, they're being irradiated with microwaves. And then their state changes after they come back down are measured. But, so the ideas are very simple, similar. You want a long interrogation. And also I should just briefly mention now, with neutral atoms, there's also what we'd call traps based on laser forces. And so they can, their experiments are much more like our ion experiments, where they're confined to a single space. But, so anyway, the answer to the question, yes, rubidium is a very viable, there's been very accurate standards made of rubidium. And I would say, I haven't kept real closely, but it's not clear whether, with full development, whether, a rubidium clock would be better, maybe even better than a cesium clock, at least with all these laser cooling ideas. So.
Okay. I'll take up the next one, sir. What is the significance of various interactions, like dipole-dipole interactions, in defining the frequency shifts and corresponding scattering associated effects in multi-level atoms?
Okay. Maybe I'm not clear, quite understand, but certainly, this is something, as I showed in our picture, we focus more on a single ion. Some of the neutral atom experiments, they have it's an array of traps, you'd say, but the spacing of the atoms can be on the order of a wavelength or less. And so in those experiments, they do have to worry about controlling the dipole-dipole interaction between adjacent atoms, and they have to do some careful calibrations on that. So it's a bigger effect for them. I would say we don't have to worry, in the ion experiments, you don't have to worry about it, but we have plenty of other things to worry about. So
Okay, sir. I'll take up the next question. Can we make measurements of the dark matter in universe with the help of atomic clocks?
I mentioned in one line that various theorists have come forward with ideas of how dark matter, for example, might affect the frequency of different clocks. And of course, it depends on the clock, because of the degree of the sharing of the different forces of nature. So I'd say unfortunately nobody's seen anything yet, but people are interested because there's some predictions out there where maybe we can see frequency shifts on our clocks due to dark matter and such. So we'll see, but certainly it's an active field. People are thinking about that. So people are certainly already have set up experiments to try to look for these and find at least gets higher and higher accuracy on these measurements. So.
Okay. I'll take up the last two questions, sir. The second last question is, can one create artificial gravitational fields to measure the frequency shift in optical clocks instead of raising the height of the clock?
Well, I think as far as anybody knows, certainly as far as I know, the only way you generate gravitational potentials or gravitational fields is with massive objects. And so that's certainly the only thing I've ever heard of. There's no kind of artificial way or,
There's one of the, I think,
generate gravity.
One of the undergrad students who have really different ideas to work upon that part. So I'll take up the the last question now. How complicated would the testing of this general relativity with the atomic clocks be? And how can independent measurement of the gravitational field and its variation be made to achieve the test? I
I
mean,
think
it's more
I
like
mean, I
everything.
described how we,
Yeah,
one way we can measure the gravitational potential redshift is just shift the relative heights of clocks. And of course, what some people dream about is, uh, having clocks that could say go near a neutron star or black hole, and there'd be a huge gravitational potential redshift there. I mean, these are, nothing is imminent here, but people certainly think about it because the fields would be so big that you could really, get, you know, very, very big effects if you could control the environment, which I think would be a big problem. But anyway, people certainly think about that. Yeah.
sure, sure. So, sir, before I conclude for today's session, any concluding remarks from your side or a word of inspiration and wisdom for the attendees from your side?
Sure. I don't know whether I don't think I have any great wisdom. I would, but one thing I can say is, I've told, students occasionally is that, first of all, you got to find something you like. If you don't like it, it won't work, particularly in science. You may be able to make money, but you're not going to enjoy your work if you don't really like it. So I guess the one piece of advice I would give is that, the students should shop around, especially in their younger years of study, and just see what's out there and find something they like. And even if they change what they like, that's fine. But whatever whatever the students like, is they should go for it. Don't hold back. You're not going to slide through. I don't know of anybody in my profession who kind of waltz through their profession, in order to be successful. A lot of hard work involved. So.
Sure. Thank you. Thank you very much, sir, for explaining such a complex experiment in such a lucid manner, which even a first year student can also understand.
Well, I
So,
hope.
yes, yes. I must appreciate, sir. It was a mesmerizing last 45 minutes. You have taken up all the questions to the satisfaction of attendees, and it's a rare opportunity for us, for all of us, to see you face to face through this webinar mode itself, and to get an opportunity to ask a question and to get an answer from you directly face to face in that case. So, on behalf of the National Academy of Sciences India Delhi chapter and the host institution, that is the Deen Upadhyaya College, I would like to thank you once again for sparing your valuable time. And I would like to thank all the attendees also for being there with us for last 1 hour. And I think it must be quite late at your place, sir. Must be 9 o'clock or maybe 9:30.
Yeah, well, that's usually not,
Yes.
not past my bedtime anyway.
Okay.
So yeah, yeah.
So
So
I
anyway,
hope,
yeah, no, it was a pleasure for me to do, and just would like to say good luck to all the students that out there that might have heard this, and wish you luck in your careers and so.
sure. Thank you. Thank you very much, sir. And if there will be an opportunity next this year or next year when we can have you in person in India, then we'll be more than glad to have you hosted out there itself, sir. That's the side from my
Thanks
side.
very much. Yeah, that'd
Sure,
be nice to
sure,
do.
sure. Thank you very much, sir. Thank you very much. So I'm
Okay.
closing this
Yep.
session. Yeah, sure.
Okay. Bye
Thank you
bye,
very much.
everybody.
Okay, sir. Bye bye, sir.